Today's lesson is on simplifying radicals. There are different approaches to take when simplifying a radical. You're free to choose any valid method that you like. I'll show you two methods, but there are more. Method 1 is actually the one that I use. There are many perfect squares shown in red. For instance, 1, 4, 9, 16, 25, etc. All of these red numbers, these are perfect squares because there's a number that multiplies by itself to turn into that perfect square. And there are obviously more than these, but these are good for starters. If you can remember what those perfect squares are, that'll be good for you. Now, when you're simplifying a radical, according to this first method, you want to determine the largest perfect square that divides evenly into the value under the square root, and then simplify as I'm about to do. So I look at 18 as under the square root. I know that 9 is a perfect square and it divides evenly into 18. So I can express root 18 as root 9 times 2. Now, a property of radicals is that I can express the square root of 9 times 2 as the square root of 9 times the square root of 2. And the square root of 9 is equal to 3. And what I've just done is I've just simplified the radical. What used to be under the radical was 18, and now it's only 2. Another question is root 32. Well, I can see that 16 is a perfect square that divides evenly into 32, so I can re-express it as the square root of 16 times 2. And the square root of 16 times 2 can be re-expressed as the square root of 16 times the square root of 2, and the square root of 16 is 4. And I've just simplified from root 32 to 4 root 2. I can even have a tough question like the square root of 800. Well, if I'm really clever, I realize that 800 is really just 400 times 2, and 400 is a perfect square. It's 20 squared. So I can re-express the square root of 400 times 2 as the square root of 400 times the square root of 2. And the square root of 400 is 20, and so I simplify to 20 root 2. But don't worry if you don't think of 400 right away. You might say, oh gosh, I wouldn't have thought of 400. But you can still get the correct answer. It just takes a little longer. Maybe when you look at the root of 800, you might say to yourself, well, that's 100 times 8. So you'd call it root 100 times root 8. Well, the square root of 100 is 10, so you've just simplified root 800 to 10 root 8. Well, that's not bad, but you can do more. Because 4 is a perfect square which divides evenly into 8. So I can re-express root 8 as root 4 times root 2. Now I still leave the 10 there. Now I can think of root 4 as 2. So instead of saying 10 times root 4 times root 2, it's 10 times 2 times root 2. 10 times 2 is 20, 20 root 2. I get the same answer I got a minute ago. So even if you don't think of the biggest perfect square right away, you can still get the right answer using method 1. It might just take a bit longer. Now method 2 is another method that some people use, and it's a really good method. When asked to simplify a radical, some people will determine the prime factors of the value under the square root. And for every 2 times that a factor appears, you can include that factor once outside the square root. And then the remaining factors are going to remain under the square root. I'll show you what I mean. Suppose we had the square root of 18. Well, that's like I can express 18 as 9 times 2. Now I can break down 9 into 3 times 3. So the prime factors of 18 are 3 times 3 times 2. Well, I have a 3, and a 2 all under the square root. I have 2 3's, so I can take them, put it outside as 1. So by putting this 1 outside, it's like the equivalent of having 2 on the inside. And then I still have a 2, 3 root 2. And that's the answer we got using method 1. Let's try another one. Root 32. I might say to myself, okay, 32 is the same as 8 times 4. I can re-express 8 as 4 times 2, and I can re-express 4 as 2 times 2. And I can re-express this 4 as 2 times 2. So what I end up with under the square root is 2 times 2 times 2 times 2 times 2. Well, these two 2's can be thought of they're on the inside, so I can bring them out to the outside as 1. So these two 2's are replaced with that 1 2 on the outside. These two 2's are replaced with that 1 2 on the outside. And then this 2's left over and it remains inside. So I'm left with 2 times 2 on the outside and root 2 on the inside. So that's the same as 4 root 2, because 2 times 2 is 4. And finally, if I have root 800, I might think of that as 100 times 8. I might think of this 100 as 10 times 10, and this 8 is 4 times 2. And so now, instead of calling it 10 times 10, I can call it 5 times 2 times 5 times 2. That 4 becomes 2 times 2, and I still have the 2. Now, if you look, I've got a couple of 5's on the inside, so I put 1 on the outside. I have a couple of 2's on the inside, I put 1 on the outside. A couple more 2's on the inside, I put 1 on the outside, and I still have that 2 inside. 5 times 2 times 2 is on the outside, and I call that 20. That's 20 root 2. All right, so you can use method 1 or method 2. It's totally up to you. For the rest of this lesson, I'm going to use method 1. But if you have another valid method, go for it. Suppose I want to simplify this expression. 5 root 72 minus root 75 plus 2 root 50 minus root 192. Well, I look at this 72 and I see 36 divides evenly into it. So I can think of root 72 as root 36 times root 2. This root 75 has a 25 that goes into it, so I can think of root 75 as root 25 root 3. Root 50 can be thought of as root 25 root 2, and root 192 can be thought of as root 64 root 3. And what's key about root 36, root 25, root 25, and root 64? What's key is that they all equal an integer. Root 36 is the same as 6, so I can call this 5 times 6 times root 2. Root 25 is the same as 5, so I can call this 5 times root 3. Root 25 is the same as 5, so I can call this 2 times 5 times root 2. And root 64 is the same as 8. Now, what I've got is 30 root 2 minus 5. This 5 times 6 multiplies, so I get 30 root 2 minus 5 root 3. This 2 and 5 multiply, so plus 10 root 2 minus 8 root 3. Now what I can do is I can collect like terms. 30 root 2, positive 10 root 2, and I bring them together. And then I have minus 5 root 3, minus 8 root 3, and I bring them together. And now it's just like simplifying. If you had 30x plus 10x, you would call it 40x. Well, that's what's happening here. 30 root 2 plus 10 root 2 is 40 root 2. Don't change the root 2. That stays solid. And here, if I had negative 5y minus 8y, I'd call it negative 13y. So similarly, negative 5 root 3 minus 8 root 3, I call that negative 13 root 3. Now, what if I have root 96 minus root 6 over root 54? Well, root 96 is the same as root 16 times root 6. Root 6 can't be simplified. Every once in a while, I'll see someone simplify root 6 into root 3 times root 2. But that's not useful, because root 3 is not an integer and root 2 is not an integer. 3 and 2 aren't perfect squares. So there's no point in doing that. Okay, we just leave it as root 6. Root 54 is root 9 times root 6. And so I see that root 16 is 4. So I've got 4 root 6 minus root 6, which is like saying 4 root 6 minus 1 root 6. And down below, I've got root 9 root 6, which is like saying 3 root 6. 4 root 6 minus 1 root 6 is 3 root 6. So my numerator and denominator are equal. So the answer is 1. And if I had 7 root 5 plus root 180 plus root 20, I can simplify 180 as 36 times 5. And I can simplify 20 as 4 times 5. Root 36 is 6. Root 4 is 2. So I've got 7 root 5 plus 6 root 5 plus 2 root 5. And collecting like terms like we said gives us 15 root 5. Now, what if we wanted to simplify a question like this? 3 minus root 2 times 5 plus root 6. Well, what we do is we expand. Some people call this FOIL. Use the distributive property. 3 times 5, 3 times root 6, negative root 2 times 5 is negative 5 root 2, and negative root 2 times positive root 6 is negative root 6 root 2. So this 3 times 5 is 15. I've got plus 3 root 6 minus 5 root 2. Now when I have root 6 times root 2, that's the same as the square root of 6 times 2. You can bring them together like that. That's a property of these radicals. So I still have 15 plus 3 root 6 minus 5 root 2, but now this has become root 12. And believe it or not, I can simplify root 12. I leave these alone, but root 12 becomes root 4 root 3, and root 4 is 2. And so this is the simplified version. All of those radicals are as small as they can be. Let's try another one. I've got root 12 plus 1 times root 8 minus 7, root 12 times root 8, root 12 times negative 7, root 1 times root 8, and 1 times negative 7. This becomes 12 times 8 underneath the radical. Root 12 becomes root 4 root 3. Root 8 becomes root 4 root 2, and I still have the negative 7. This is root 96. The root 4 has become a 2, so I've got 7 times 2 times root 3. Root 4 has become a 2, so I've got 2 root 2, and I'm still subtracting 7. This can be simplified as root 16 root 6. 7 times 2 is 14, and I have these two terms remain the same. And finally, I have 4 root 6 minus 14 root 3 plus 2 root 2 minus 7. Again, I've seen people do this where they want to get a 4 root 2 root 3 in there, but that's not useful. There's no reason to do that. They're not like terms with any of these, so there's absolutely no reason for that. So this is our final answer. All right, let's get to part C here. Negative 4/5 of the square root of 250. Well, the square root of 250 is root 25 times root 10. And I still have the negative 4/5 there. Now, if you think about it, this is like saying root 25 over 1 and root 10 over 1. So I can multiply negative 4 times root 25 times root 10 in the numerator and 5 times 1 in the denominator. Okay? Now, this root 25 is the same as 5. So I've got negative 4 times 5 times root 10 over 5. Negative 4 times 5 is negative 20. So I've got negative 20 root 10 over 5. And I've seen people do this. They really want to involve that 5 twice. I've seen people say negative 20 over 5 is negative 4, and 10 over 5 is 2, and they do that. That's incorrect. Think of this more as if I was saying something like negative 20x over 5. If you thought of it that way, you'd leave the x alone and you would tell me the answer is negative 4x. Well, that's what it is. You're not changing that root 10 anymore. It's in place. Okay? And that is your final answer. All right, now what if we had 2 root 15 times 3 root 60? Well, multiplication is commutative, and so what that means is all we're doing here is multiplying. So I can multiply the 2 with the 3 and the root 15 with the root 60. 2 times 3 is obviously going to be 6. Now, root 15 times root 60 is the same thing as the square root of 15 times 60, which is the square root of 900. The square root of 900 is actually 30. So I ultimately end up with 2 times 3 times 30, which is 180. And we'll end it with a couple of word problems. Let's determine the length of the diagonal of a rectangle that has side lengths of 6 and 4 centimeters. So here's a side length of 6, and here's a side length of 4, and I've got a diagonal up the middle. Well, since it's a rectangle, we know that's a right angle. So we can use Pythagorean Theorem. D squared equals 6 squared plus 4 squared. 36 plus 16 is 52. That means if d squared is 52, that d is the square root of 52. And 52 is 4 times 13, and I can simplify it as 2 root 13. And finally, last question here. What if we have 2 points on a graph and we want the length of the line segment, it's helpful to remember the formula for distance that you might have learned in grade 10. Square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. So we just go 6 minus negative 2 quantity squared, negative 3 minus 1 quantity squared. This 6 minus negative 2 is 8, negative 3 minus 1 is negative 4. I'm squaring the 8 and I'm squaring the negative 4, which gives me 64 plus 16, which is all under the square root, which is root 80. That simplifies to root 16 root 5, and root 16 is the same as 4. So we get 4 root 5 as the length of that line segment.